Okay. I hope everyone is able to see the screen and you're able to hear me all right. Yes?
Yes, ma'am.
Okay, thanks. All right, so we extended postulate 1 to say that quantum states are represented by density operators, which are operators on the system Hilbert space such that trace rho is 1 and rho is positive semi-definite. Okay, and we kind of gave some examples of this from the measurement scenario and so on. Now, remember we said that if you have such an operator, there is always a way to associate with such a density operator. Why my pen is acting up? An ensemble of pure states, right? So these operators which have this property that they are positive semi-definite and have trace 1 can always be associated with an ensemble of pure states. The simplest way to do this association is to diagonalize the operator, and then you can represent it as an ensemble of its eigenstates weighted by the eigenvalues. Conversely, if I have any set of pure states, which is basically some set of states psi I, right, which are mixed or picked according to some probability distribution pi, right? 1, right? And so then you can always show that this operator, which you write down like this, as the weighted sum of the projectors onto these pure states satisfies these properties. Okay, so first note that this is the definition of the density operator, positive semi-definite trace 1 operator. Second, such an operator can always be expanded like this as an ensemble of pure states or as a convex sum of projections onto pure states. Okay. Then we spoke about pure versus mixed states, and we said that so I had left last class by asking you to identify what is the density operator associated with plus plus. Yes, I think this is what I had asked last time. Yeah. What is the matrix associated with this? Did anybody work this out? Can you work it out now? Okay, let's do this more, okay, before I get into pure versus mixed, let me do some examples now. Okay, let me start with 0, 0 first. Okay, I have a single pure state. Okay, what is the density operator associated with this? What is the matrix representation? Yeah.
1 0 0 0.
Okay, good. So note that a qubit density operator, which means a density operator that represents states of qubits, will always be a 2 cross 2 complex matrix, right? The complex 2 cross 2 matrix anyway. So just keep this in mind. So the second operator I wanted you to write down was plus plus. What is the density operator associated with this?
One by 2, 1, 1, 1, 1.
Yes, good. Do the others agree?
Yes, ma'am.
Okay. What about minus minus? Let's call that sigma.
Will be 1, -1, -1, 1, and 1/2 will be outside.
Good. Okay. What is rho plus sigma?
Identity.
Indeed, identity, which is what it should be, right? This is a projector onto one orthogonal state, projection onto another orthogonal state. It's a two-dimensional space. So if I sum it up, I should, of course, get identity. Right. Okay. Now, what about the ensemble, which has ket 0 with probability half and ket plus with probability half? The ensemble, let's say, of the two-party game that we've discussed. So the density operator would be written as half 0, 0 plus half plus plus, right? What is this?
The first term will be 3/2 and the rest term will be 1/2.
The first entry is 3/2.
And the rest will be 1/2.
I think you're missing a factor of half.
Yes.
So let me write this as 1/4, 3, 1, 1, 1. Can folks tell me if this is correct? Yes? Okay. So the point I'm trying to drive at now, among these, you know that some of these are pure states and some of these are mixed states, right? Which are all pure states? This is a pure state. These two are pure states. And this really is a mixture. Okay? But once you start putting down this matrix representation, especially because you work in a specific basis, right? Remember that the reason that I have a non-trivial matrix form for this plus plus projection is because I'm in the 0, 1 basis, right? This is a representation in the 0, 1 basis. You can, of course, think about what will happen if I go to the plus minus basis. What will these projections look like? Okay. So the point is, how do I, looking at a matrix form, if I give you this matrix form of a density matrix, how do I know whether the state is pure or mixed? So that is where the rho squared test comes in. Okay. So pure versus mixed, right? Just by looking at the density operator, how do I decide if the state is pure or mixed? Well, you look at trace rho squared, and trace rho squared is 1 if and only if rho is a pure state. Okay. Now, like I said last time, this is easy to prove. I will just write down a 2-line argument for this. So if rho is pure, that means you can write it simply as a projector onto some pure state, right? Then trace rho squared is the same as trace rho, and therefore that is 1. Yes. If rho is a mixture of this form, then trace rho squared, can you quickly evaluate what this will be?
Sum of phi I square if psi i's are orthogonal.
Sum over I of what?
Phi I squared.
This is P, sorry, probabilities. Okay. This is what you're calling.
Pi
Yeah.
squared.
Pi squared. You said if the psi I are orthogonal. Why should the psi I be orthogonal for this? Oh, okay. I see,
Like
because
the
you get
Pi
these
Pj
yeah,
terms
cross
should.
terms. Okay, fine. If you don't have the cross terms, I mean, if they're not orthogonal, what is the general statement? I think I wrote this expression last time, right? So it will be psi I, psi j mod square. Correct? and this will be actually PIPJ. Fine?
Oh, ma'am.
Yeah.
Actually, I'm a little confused with this mod square. Should it be mod square?
Why should it not be mod square?
I mean, I was trying.
So if I go through the steps of this, then this is trace of, there'll be two sums, right? Because I'm taking the square of this PIPJ. There is psi I, psi j, correct? Trace of this whole thing. Now, what is the trace of this whole thing? So I keep emphasizing this, guys. The trace mechanics with the bracket notation is very important for you to familiarize yourselves with this. I've given one question in the assignment, but in general, it should be easy for you to see that this leads to that. Okay? Because we're going to constantly do things like this. Okay, so you pull the sum out. Okay, so then I have sum over ij, pi, pj are numbers, so I pull them out. Trace, I have psi I, psi j, psi j. Correct. So now Neelkan, do you see? Psi j is a number, so that comes out.
Oh,
So I'm left
yes.
with.
Yeah, got it.
So then I have psi I, psi j, the inner product, and then I have trace of psi I, psi j. So yeah, actually, I don't know if this particular question is in the assignment, but in general, if I have two pure states, psi and phi, what is trace of psi phi? Yes? Pop quiz. What is trace of psi phi?
The inner product of psi and
Psi
pi
and
and psi.
phi.
In which order? That's very important. Is it this?
Phi will be kept and psi will be.
Or is it this? MCQ, option A or B?
Second one?
Indeed, it's the second one. So why are you asking me tentatively? You should be confidently telling me it's the second one. Okay. So please, if you have not worked this out, I repeatedly keep telling you, check this for yourselves with an orthonormal basis. Okay. And once you have convinced yourself, remember this fact, right? Okay. So this, the order gets flipped, okay, because you'll essentially, it's like inserting inserting an expansion of identity in some orthonormal basis. And that's what taking the trace is, okay? So this is very important. Please keep this expression in mind. I'm decorating it with multiple boxes, etc. But the point is, so then this here becomes sum over ij, pi, pj. This becomes psi j, psi I. So that is indeed mod psi I, psi j squared. Okay. All of this was to say that this quantity, therefore, if it's a mixed state, is strictly less than 1. Okay. And I've said only if it's a pure state. So I think that requires that we show that. So in other words, if you look at this sum, right, and you ask, when can this sum be equal to 1, right? So when can trace rho squared, which is equal to, in general, this sum, right, of this form, pi, pj, psi I, psi j squared, when can this be equal to 1? Well, that will demand that, first of all, these are all coefficients which are smaller than 1, right? And for a given j, this sum is 1, because that's the expansion, well, okay, not necessarily, but the point is, you can say that because this is a convex sum, right, weighted by some kind of probability distribution here, right, this will be 1 if and only if this, rather this probability distribution, so this becomes equal to 1 if and only if this PIPJ becomes equal to a delta distribution essentially. So this should become not just delta ij, yeah, well, it just becomes a delta distribution. So is equal to 1 for some I is equal to j and 0 for all other I and j. Okay. All right. So this is a sort of argument to justify that trace rho squared is 1 if and only if rho is a pure state. Basically, if you assume that it's a mixture of this form, you will get a sum of terms. So you can think of these coefficients here as some numbers, right? SomeCij's, positive numbers, which you're weighting according to some probability distribution PIPJ, right? So if you now then ask when can this be 1, since these are all positive numbers between 0 and 1 and these are probability distributions, this can be 1 if and only if this probability distribution becomes a delta distribution. Okay, so I hope this argument is clear. So now if you go back and look at the examples we wrote down 1, 2, 3, then you will notice that in this case you can check that trace rho squared is not equal to 1. In every other case, trace rho squared will be 1, and in this case it will be strictly less than 1. Okay, so trace rho squared is considered a measure of purity of the density matrix. By the way, density matrix is the same as density operator. Okay, and the second point is that 1 minus trace of rho squared, okay, which is in some sense the loss of purity, right? Because if it was a pure state, then trace rho squared will be exactly 1, right? If it's not a pure state, it's something which is away from 1, right? So this difference is often called an entropy. It's called the linear entropy of the state rho. Why is this an entropy? Because it's a measure of how mixed the state is, right? And if it is 0, then the state is pure, right? Because if it is pure, then trace rho squared is 1. There is no deficit from 1. The entropy is 0. Those of you who've done some probability theory or statistical mechanics will know that this is a classic definition of an entropy, right? Because the entropy is 0 for pure states, it's 0 for delta distributions, right? And for every other state, it is something that is larger than 0 but less than 1, right? Something that lies between 0 and 1. Okay, so this was about purity and entropy or mixedness. Okay, now the next thing that I want to discuss is this ensemble description of a density operator, right? So the question that in fact you should have asked me is this ensemble description of a density operator unique? Meaning, given a rho, is there only one way to associate such an ensemble of pure states with the density operator? What do you think?
No, ma'am.
Why not?
Because we can have multiple bases, I mean different bases. So we have different representation.
So that's, yeah, so your intuition is partly correct and partly wrong, right? So first of all, note, like one of the students answered when we were doing this problem, this proof, so to speak, this need not be a basis. Okay, the psi I, psi j need not be orthogonal. Okay, so this is not the same argument as saying that every matrix can be represented in different bases. Because when I represent matrices, if I represent a general matrix, okay, let's say it's Hermitian, okay. Now it can be represented in terms of its eigen basis and it will be diagonal, no doubt. But if I represent in a different basis, then note that you will have cross terms, okay. You will have Fi, Fj. This is not a projection on a pure state. This is an outer product of some Fi with some Fj, but it is not an outer, it's not like an ensemble description of this form, right? So this is the eigen basis representation for any matrix. Now in any other basis, this is what will happen, right? I will go from a fully diagonal representation to a matrix which is non-diagonal. But that is not what one is talking about here when one says ensemble description. So let me give you an example of what I mean by having multiple ensembles associated with the same density matrix. I hope this is clear that this is not about standard basis change of basis. Okay, so here's an example. So consider a matrix density operator of this form, which is 3,4,0,0 plus 1,4,1,1. First of all, check that this is a valid density operator. Means what? It is indeed a sum of projections onto pure states, mixture of pure states. 3 by 4 plus 1 by 4 is 1. So trace of this will be 1. It's a valid probability distribution, etc., etc. Right? So you have to do that sanity check for yourself. All right. Now let us define two states. So there is a ket A, which is some superposition of 0 and 1. Okay. So what is this? Is root 3 by 2 ket 0 plus 1 by 2 ket 1. Right? This is a valid pure state. How do you check that something is a pure state? You have to make sure that it's normalized. Okay, please check that the inner product is 1. Always when you write down a density matrix description, it is in terms of normalized pure states, right? Okay, fine. Now I'm going to define a second state, ket B, which is a similar superposition, but with a different relative phase, with a minus sign. Okay. Now, of course, check that B is also a valid pure state. But now please tell me what is the inner product between A and B?
One.
1.
1 by 2.
One. Yeah.
1 by 2. What is the inner product the other way around? BA.
It will be the same.
One by.
Indeed, it will be the same. Good. Okay. I was just checking. See, these are real coefficients, right? So when it doesn't matter which way I do the bra and the ket for this one. All right. So the point I'm making is A and B are not orthogonal. Okay. A, B are not orthogonal. Okay. So I have one representation of this density matrix in terms of projections onto a pair of orthogonal states. So now obviously I'm going to write down. So let me write down some rho tilde, which is an equal mixture of A and B. Okay. Now please work out what this looks like in terms of 0 and 1. So if I were to expand this in terms of ket 0, ket 1, what does this look like? You know the relation between A and B, okay? It's this and this. Please substitute and tell me what does this look like in terms of 0 and 1. Quick.
Ma'am, it's the same, right? 3 by 4 projection operator on 0 plus 1 by 4 projection operator on 1.
Yes, indeed. So that's precisely the reason why I wrote down this also. So this is the same as rho. Okay, so what have we done? We now have two equivalent representations for the same density matrix. Two, I want to say different ensemble representations for the same density matrix, right? So rho is 3 by 4 0 0 plus 1 by 4 1 1. It is also half AA plus half BB. So another way of saying it is this ensemble which has 3 by 4 0 and 1 by 4 1 is the same as the ensemble which has state A picked with probability half and state B picked with probability half. Right? I hope you see that. Now of these two, one is a diagonal representation. Which is a diagonal representation?
First one.
The first one is a diagonal representation because 0, 1 is an orthonormal basis. A, B are normalized pure states, no doubt, but they're not orthogonal. So the second part is not a diagonal representation. The first part is a diagonal representation. But you have these two equivalent representations for the same density matrix, right? So this brings us to a very important result in quantum theory itself, specifically in quantum computation and quantum information, which is that, first of all, so let me say this. So this is often called, so there are several people's names associated with this theorem. So I'm going to state a theorem about this fact that different density operators, the same density operator can be represented in terms of multiple ensembles of pure states, right? So this is the SHJW theorem. Okay. So S stands for Schrödinger, who was the first to notice that you can actually have multiple decompositions for the same density matrix. And when I say decomposition, again note, I am not talking about changing the basis, right? For example, I could write this down in the plus minus basis, but that will not be an ensemble decomposition. An ensemble decomposition means that you have a bunch of pure states and the density operator is represented like this as a weighted sum of projectors onto these pure states. Okay? It does not entail things like this, where if I change the basis, I'm going to end up with some, outer products like this. Okay? This is not an ensemble representation. Okay, this is simply a matrix representation. An ensemble representation or an ensemble decomposition means that you're expanding or representing this density operator as a probabilistic sum of pure state projections. Okay, and Schrödinger was in fact the first to note this. More recently, once people started thinking about quantum information and computing, etc., then these gentlemen sort of revived this theorem. So this is Houston, Joza. This is the same Joza of the Deutsch-Joza algorithm, and Wouters. And you'll often find Wouters' name figuring in a lot of early results in quantum information theory, right? So this is the set of sort of people who worked on this idea that, first of all, the ensemble representation of a density matrix is not unique. And I have convinced you with this example that that is indeed the case. Okay. So in particular, the different ensembles, right, are related in a particular way. So the different ensembles associated with a given row are related to each other. So you can't write down arbitrary sets of, so how do I identify, right? So how did I arrive at this A and B, right? And how did I know? I mean, I gave this to you as an example, right? But surely I have back calculated something, right? So how did one get to this A and B, which are related to the 0 and 1 in this particular way, to show that they both correspond to the same density matrix? So there is clearly some mathematics at play here. Different ensembles associated with the same density matrix are related to each other as follows. So that's the main crux of this theorem. So it says that two ensembles, so I'm going to refer to one ensemble with a set of projections psi I, pure state psi I, weighted by probabilities pi, and another ensemble with probabilities qj and corresponding pure states phi j. Okay, so these two ensembles are that they generate or they represent the same density matrix rho if and only if the states are related in a particular way. The states psi I and the probabilities pi should be related in a specific way to the states phi j and the probabilities qj. What is the specific way? So it says that square root pi psi I is equal to sum over j. So let me now write it like this. So I need to now put some numbers to this. So let me say I runs from 1 to n, okay, and j runs from 1 to m, okay. So this should be related to these. So I'm going to put a different index here, k going from 1 to p, okay, uij square root qj phi j. So what is p here? So p is whichever is the larger of m or n. Okay. And what are these uij's? The uij's are entries of a unitary matrix. Uij are elements of a and uik, right? Okay. I'm just trying to keep the indices clean. Okay. P cross P unitary matrix. Okay. So the idea is that these two pure state representations are the same or refer to the same density matrix if and only if the two sets of pure states, namely the phi k's and the psi i's, are related to each other via a set of coefficients which are elements of a unitary matrix. Right? So if I write down a unitary matrix U with entries little u11, little u12, etc., 1p, 21, etc., 2p, p1, etc. So this is a unitary matrix. So the matrix of coefficients has to form a unitary matrix, which means they must satisfy the properties that the elements of a unitary matrix should satisfy, right? Okay, so any questions on the statement of the theorem itself? Yes, no, completely lost?
Ma'am,
Yeah,
P is max of Mn, right?
yes,
Now suppose N is greater than M.
yes,
In this case, what will be this ik for?
indeed, good. So that should be the first question. Yeah, so now these two sets need not have the same number of elements. That's what one is trying to say. That's why one is writing it in the most general form. If n is equal to m, there is no issue. Like the example I gave above, right, where both ensemble descriptions had exactly the same number of pure states, there is no issue. This is just a square unitary matrix. But now if I want to get this unitary property, I need a square matrix. So what do I do? So you said n is smaller than m. Then you append zero vectors, right? So you know that every vector space has a zero vector, the all zero vector, right? So you simply append zero vectors. So here I should add a line which says append. So nothing happens to the unitary matrix, by the way, right? Because the unitary matrix elements are constrained. They have to satisfy some property. I'm just going to write down what that property is, right? But what you have freedom to do is to add zeros to whichever is the smaller set. So if the n set is smaller, so append zero vectors to the smaller ensemble. Okay? And that's how you will complete this unitary matrix, so to speak. Okay? So I hope that answers that question. Second point to note is that I'm weighting the pure states by the PIs. So what am I doing now? Square root pi times psi I is not a normalized state. Psi I by itself is a normalized state. So I'm actually saying that the relation is not just between psi I and phi k, but somewhere the p's and the q's also have to figure in this relation, right? Because so it's in some sense it's a relationship. So remember when I write this down, so what I mean is this, right? So I have rho is sum over I pi psi I is the same as sum over j qj phi j, right? So when I write this down like this, I'm saying that I have to actually what is related by a unitary transformation is not the psi I and the phi j. That would be a basis transformation. If these guys are orthogonal and so on, right? That'll be like a basis transformation, let's say. But what one is relating is actually these two states, psi I tilde with phi j tilde, where the tildes are unnormalized states now. So root pi psi I, I'm going to call psi I tilde, and root qj phi j, I'm going to call this as phi j tilde. So I'm relating now actually the unnormalized states, right? That is what is being related by this unitary transformation. Okay. So now let's see what is the properties of this uik. But so I'm going to try and prove this theorem now for you. Okay, so it's going to take us some time to get to the mechanics of this. But what is the physical implication of this? Why is this important? Why did people like Schrodinger and so on worry about this? Right? So the reason this becomes important will become very clear when we start looking at entanglement, which hopefully by next class I will start. Right? So when I start looking at entangled states, right, it will turn out that the local description of these entangled states are mixtures. They are not pure states. And the fact that the same mixture can be expanded in different ways will say something about the locality versus non-locality aspect of this. The fact that you really cannot extract information from an entangled state, that having an entangled state does not allow you to extract information, instantaneously or, faster than light and so on. That cannot happen because of this very important statement that you can have two different ensemble representations of the same density operator. Now, recall that post-measurement states are essentially density operators like this. So, whenever you think about these post-measurement states and whether you can identify these states and so on, you always have to keep at the back of your mind that the same operator can be represented as multiple pure states. Okay? So, we'll see the implication of this more clearly when it comes to the entangled state and what is the local description of an entangled state. Okay. All right. So now to prove this theorem, so what I'm going to do is I'm going to prove one direction and I'm going to indicate how the other direction is proved, and I'm going to leave it as part of assignment 2. As you can see, I'm already working on assignment 2. So please finish working on assignment 1 quickly. Okay. So let's do one direction first. Okay. So so like I said, I defined the psi I tilde. So that's what I defined here. So this is root pi, psi I. Because the relationship is really between these sets of unnormalized states. Okay. And suppose we are given that this set of states psi I is related to the other set of states phi j via a unitary transformation. Okay. So let me just put j here now that it's clear that you have to append zeros to whichever is the one which has smaller entries. Okay. So this is this. Okay. Where uij are elements of a unitary matrix. So this is like the example we did, where I gave you two sets of states. I showed a relation between them, and then you told me that, oh, actually they correspond to the same density matrix. Okay, that's what we're trying to do first. We're trying to say that if I have two sets of unnormalized states, which are related like this, via a unitary matrix, the elements of a unitary matrix, then what do we have to show? Sum over psi I tilde bracket is the same as sum over phi j tilde bracket, right? Okay, now what is the property of the element? What do these uij satisfy? So if U is a unitary matrix, let's recall that first. U dagger U is identity is U dagger, right? So what does this entail? So let us now write this in matrix form, right? So we said Uij are the elements of U, right? So if Uij is Uij, right? They are the elements. Then what is U dagger Ij? What are the entries of the adjoint complex conjugate, I mean the transpose complex conjugate? Yes?
UGI conjugate.
So this is U star Ji. Okay, good. So I hope everyone first understands this, because I don't think I wrote this out explicitly when I defined the adjoint, right? Because what am I saying? The ijth element of U is Uij, then the ijth element of the adjoint will become the jith element of U, right? Because we're doing the transpose and the complex conjugate. That's all, right? Okay, so now U dagger U, what is this product? Introduce a third index K. So this is U star JK U K. So what do I want to say? Yeah, UKI, let me say. Will this lead me to trouble? Okay, anyway, doesn't matter. So this, what is this? So what am I writing now? I'm writing the, okay, let me write the ijth element rather than the jith element. Actually, I am writing the I. Okay, let's see. So let's write the ijth element of this. Okay. So what should this be? This should be sum over k. Let me do this slowly. U dagger ik u kj, right? So this will become sum over k uki star ukj. Correct? Are you all with me? And what does this become? If it's a unitary matrix, then this has to be the ijth element of the identity matrix, which is nothing but delta ij. Correct? It's 1 on the diagonals and 0 everywhere else. So this is the first relationship. UKI star UKJ is delta ij. Okay. And what's the other way around? U dagger ij, sum over k uik u star jk, and this is also delta ig. Okay. So you see that this works both ways. All right. So let's keep these two relations in mind, and let's call these two relations as star. Right? This is the property that the elements of a unitary matrix satisfy. All right. So now we get back to this proof. So we are given that we are given two sets of states. Rather, we are given two ensembles, which is pi psi I and qj phi j, such that square root pi psi I is related to the j's via some unitary matrix. Right? Now, this is what we called as psi I tilde. So let me write this in the tilde notation as well, and phi j tilde. These are the non-normalized versions of these. So now, what is sum over I? Psi I tilde in terms of the phi I tildes. So now you should see that this follows very easily. Remember, now I'll have two sums. So I'll have a sum over j and a sum over k. So I will have uij star, right? I'll have uij. Let me write this. J phi j tilde phi k tilde u ik star, right? So this becomes, I forgot the sum over I. Is this step clear to everyone? So I am replacing the psi I with this part, the first part, which is sum over j uij phi j tilde. The adjoint ket, the bra vector, right? I'll have to use another index. So I'm using the k index here. So that becomes the bra phi tilde k with the corresponding complex conjugate here, right? So ik will become ik star. And then there's an overall sum over I, correct? So now what do we do to show that? So now you see this is not an ensemble representation, right? This has the so-called diagonal terms, right? This has the j not equal to k terms. So what should we do to show that you actually get an ensemble description here?
Sum over I, Uij, and U conjugate Ijk can be written at delta Jk, right?
Indeed, exactly. So that's the point. Very good. So you take the sum over I inside now, okay? And you look at Uij, Uik star, right? And then I have phi tilde j, phi tilde k, correct? So now go back to these relations. So this, of course, the indices are all mixed up here, right? I mean, it doesn't matter. So what is k here becomes I here, okay? Actually, the first relation. What is k here becomes I in our case. What is I and j become j and k, right? But I hope you see that unitarity implies that this should become delta jk since u is unitary. And therefore, I end up with sum over j comma k delta jk phi tilde j phi tilde k, and then this is nothing but sum over j okay. So that's it. So what have we shown? They both correspond to the same density matrix rho. So if I have two sets of states with probabilities pj qj such that square root pi psi I is related to square root qj phi j via a set of unitary coefficients belonging to a unitary matrix, then the two ensembles represent the same density matrix. So we have proved one way of the Schrödinger-Houston-Joseph-Wouter's theorem. That which part have we proved? We have proved the if part, right? We have proved that if we have these two ensembles related like this via the coefficients of a unitary matrix, then these two ensembles indeed correspond to the same density matrix. The other direction, which is to say that if I have two ensembles which correspond to the same density matrix, then there must exist a unitary matrix such that they are related like this. I'll give you the proof sketch next time and leave the details to the assignment. Okay. But so far, is this clear? Is this one direction of the proof clear? Questions? No questions? Okay. Yeah, so you will have to work this out. I mean, this is where this, I don't know, I feel like this online way of doing things sucks. Because if it was on a blackboard, I don't know, I somehow find it easier to stare at a blackboard and learn a new theorem or a proof. But unfortunately, we are in times where I cannot write this on a blackboard and show you. But I hope you followed the proof as I was discussing it, and I hope you will work it out yourself. Like I said, this has physical implications because when you say that you consider a density operator, you have to keep in mind that there is no unique ensemble description of such a density operator, right? So this has consequences. All right, so let me stop here. Can I stop sharing? And any further questions? If not, I'll see you on Thursday.